Hello everyone, welcome to our Calculus 3 online course. Today in this video clips I'm going to talk about three-dimensional space and vectors in three-dimensional space. So in order to study about 3D means three-dimensional space. Sometime I'll relate it back to 2D, a two-dimensional space. It's going to be easier for you to link and then study for three-dimensional space. So first, let's start with the coordinate system in 3D. Okay? So let's recall what you learned before in 2D. So pretty much you have two dimensions to represent a point on the plane or a function on the plane. We use what? The x-axis and the y-axis, right? And for every point on the plane, you have two coordinates called x, comma y. X tells you how far it is from the origins, and y will tell you how high it is from the origins. Okay, so you got two dimensions to represent a point. Now we develop our study a little bit deeper. Instead of having only two dimensions, what if you have an object on the three-dimensional space, not just x and y? We add one more dimension to our study. It's called z. So as in this 3D, I'm gonna kind of add one more this way. Okay, so you have to use your imagination a little bit more to help it better. This is called the x-axis, the origin right here. This is the y-axis, and this is the z-axis. Okay, those all three are not on the plane. Actually, this is like one dimension. This is out, and then I tried to draw a three-dimensional object on a board. Just look this way, and this is the x-axis, y-axis, z-axis. They all perpendicular to each other. Okay, it's that. And if you have a point on the 3D space, is denoted by x, comma y, comma z. Okay, this point got three coordinates. Okay, make it clearer. Then let me try to project it down to the plane. So this is x-axis, y-axis. Erase that twice so I have room to draw. Okay, if that makes any sense to you. This is the point on the space. X, y, and z. Alright? Okay? And this is the z value. This is the y value right here. And this is the x value. You project that point down into the three plane, you have x, y, and z. Alright, so pretty similar to two-dimensional space, just require our imagination a little bit different. Okay? And so, say 2D right here, 3D, a point is x, y. A point in 3D is going to be x, y, and z. X dimension, y dimension, and z dimension. Okay? And in 2D, you have, say, let's try 2D is short. Say y equal to 5. It's going to be a straight line, right? So in 3 dimensions, if you draw like y equal to 5, it's not a line anymore. It's going to be a plane. Y equal to 5. The whole plane. This way. Alright? Let's see something similar. How about distance? Say you have 2 points. Then the distance formula in here is what? Distance is going to be square root of x1 minus x2 square plus y1 minus y2 square in two-dimensional space. You guys studied this in college algebra, I think. In 3D, and you add one more dimension to it, so it's just square root. What? x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. I'm talking about the distance between the 2 points on the plane, okay? Or the distance between the 2 points in the space. So you have 2 points on the plane in 2D, okay? You have 2 points. This is x1, y1. This is x2, y2. And you want to calculate this d right here. This is the formula. And similarly, if you got 3D and you got 2 points on it, this will be the formula. Very similar. Just add one more component to it, the z component, okay? That is for the distance. Very similar. And one more, the equation of the circle. equation of the circle. On 2D, So 2D right here, the circle, center, say center of the origin. It's gonna be what? X squared plus Y squared equal to R squared, right? Now, development to 3D is not a circle anymore. So let me write here, circle, X squared plus Y squared equal to R squared. 3D is going to be a three-dimensional object. You have something called a sphere. Sphere is what? X squared plus Y squared plus Z squared equal to R squared. This is a circle, center at the origin, radius R. See, flat circle like a dish. And this is a sphere. It's like a ball. What you have is this. How do I draw it? Let's just draw the ball. It'll be easier. Okay. It's like a ball. And of course, if you shift the ball around or shift the circle around to a new center, like h complicated what? X minus h squared plus y minus k squared, square outside, equal to r squared. This is also a circle on the two-dimensional space. Center at h comma k instead of the origin, right? So center at h k in general, and radius r. You do the same thing here. You got to h k I j k l h k l. Then you have a new center sphere with new center. X minus h squared, y minus k squared, z minus l squared equal to r squared. Still the same sphere, just move to a new center. That's the point. Center at h, k, l. This is center. Okay? So, not much of the very first section for our course. Just try to introduce you the idea of three-dimensional space that we can draw. So we have 3D object instead of just two-dimensional, like what we usually learned before. Okay. Let's move on to the main thing for the day. I'm going to talk about vectors. Those are on section 12.2 and 12.3. Okay. What do we mean by a vector? So geometrically, vector, you guys should think of an arrow. This is called the initial point, okay? Terminal points, or this is called the arrow right here. It's like the end point, okay, arrow. Vector has two things associated with it. The magnitude of that arrow, which represents like the strength, okay? And the direction, okay? Two things. Usually people denote vector by a lowercase letter with an arrow on top of it. So we would call this is a vector u. Okay? And the length or the magnitude of u is denoted this way with the absolute value. Okay? Tell you the length of it. And this is a vector u. Okay? I bet that you took what's called trigonometry. We did talk about vector in two-dimensional space already. So in here in Cal 3, we still come back to one vector again, but instead of two, now that we talk about vector in 3D. Okay, it's the same thing, just one more dimension. Okay, so if you have a vector, say vector u right here, we use the same u right here, and you have another vector v. Vector v. And if the two vectors are parallel to each other and have the same magnitude, we technically say that those two vectors are the same. Okay? If they have the same direction and same magnitude. Okay? So it's same vector. In other words, you can just move vector around without rotating it, shift the same vector around the space, you have the same vector. It won't change. As long as it preserves the same length and the same direction, then you have the same vector. Okay? Okay, now what if I have two vectors? and you want to do some algebra with it. This is my vector u, and this is my vector v, the vector v right here. Okay. What if I want to do something like u plus v? As I said before, if you shift the vector around, it's going to be the same. So I'm going to shift vector v such that the initial point of v right on top of the terminal point of u. Okay, this is my v. Make sure it's parallel. Okay. This is v. Same v. Okay. So u plus v, you have a new vector where the initial point is starting at the initial one of the first vector, and the end point at the end point of the second vector. So this is, we write it u up here. It's going to be u plus v. This is one way to think of it. You just move the second vector so that the initial point is on top of the terminal point of the first vector, and then connect triangle. Or another way to think of it. Let me copy my vector u is right here. Okay. Instead of moving vector v this way, I can move vector v this way. V right here. It's the same. Okay. So instead of having that v, don't think of this v. I'm going to use parallelogram in here. So I'm going to construct a parallelogram. All right. So v here or v there is the same. The sum of two vectors is this u plus v. You guys see it's the same. You can have v right here or v right there. Vector u plus v is still the diagonal. Okay, that's how you add using geometry. And what do we mean by minus? Well, the opposite, right? So if v is right here, goes right here. This is my v. Negative v gonna be this. Same direction. I'm sorry, same magnitude, but the opposite direction. Same vector. Okay. Negative v. Okay. And now you have negative v. It makes sense to have something like u minus v. Just simply add the opposite of v. It's called u minus v. Okay, that is introduction to something called vectors and the magnitude. I showed you that already. Okay, now let's talk about vector algebraically instead of using geometry. Okay. So in 2D, as I said, we can move the vector around, so we will always set the vector such that the initial point is right at the origin, right? And then the end point is somewhere at the point. So let's go to u right here, then the initial point, the origin. And the end point, say at 3, 5 in parentheses. Okay, means what? This is 3, and this is 5. Alright? So we're going to denote vector u this way algebraically. Equal to an angle bracket. 3, 5, angle bracket. We denote that the vector with origin point at the 0, 0 point, and the tip is at 3, 5. Okay? And similarly for 3D, you have, let me draw 3D down here. So you add one more dimension into it. This is x axis, y axis, and then z axis. I have a vector u right here. It's gonna be say 3, 5, and 6, for example. Okay. And what? X is 3, y is 5, and z is 6. Instead of 2, now I have 3. Okay. So let me draw another u right here in 3D. 3, 5, and 6. All right. So in 2D, how do you calculate the magnitude or the length of that vector? Use the distance formula, right? So magnitude of u is 3 minus 0 squared, which is 3 squared, and then 5 minus 0 squared, take square root. So really, square root of 3 squared plus 5 squared. And similarly, the magnitude of this one is going to be square root of 3 squared plus 5 squared plus 6 squared. And then you have a calculator, you should be able to calculate those numbers. But it was just the idea, okay? So in general, if you have a vector u, this is a, b, c, or x, y, z, however you call it, the magnitude is calculated this way. Square root of a squared plus b squared plus c squared. All right. What about adding two vectors algebraically? Say I got vector u 3, 5. This is 2D. Okay. Say I got vector v. How about vector v? How about 1, 2? You add the two vectors, u plus v. You just simply add those value components wise. So it's gonna be 4, 7. Oop, this is angle bracket. Okay. That's parentheses. You guys see where I got 4 from? 3 plus 1 is 4. 5 plus 2 is 7. And same thing for 3-dimensional space. You just add x to x, y to y, and z to z. So in general, if I have u is x, y, z, and v vector, right, is a, b, c, then u plus v vector will be x plus a, y plus b, and z plus c. And of course, guess what? This is u, right? So negative u is going to be negative 3, negative 5. You put a negative in front. The opposite. Okay. Very special vector. Vector 0. This is not a number 0. This is vector 0. What do we mean by this? This is a vector with dimension whatever. What is the length? The magnitude. Magnitude is 0. Okay? It has no length. It has any dimension you can think of as well. Say 2D. It's the point right here. 3D, see the origin. Okay? Now let's talk about the orthonormal basis of a vector space. Well, I always try to get back to the 2-dimensional space, make it easier for you guys to start, and then I'll move on to 3. Okay? So if 2 is x-axis, the y-axis, the origin right here. We define the vector, say I, this way. 1, 0. 1, 2, 3. This is my vector I. 1, 0. Right? This is vector I. Okay, and we define vector j as, this is angle bracket, and then 0, 1, and this is vector j. And you know what? Every single vector in the 2D space can be represented as a combination of I and j. See why? For example, u, we call that as what? 3, 5. You can think of u as 3, 0 plus 0, 5, right? Because we don't have to add the two vectors. 3 plus 0 is 3. 0 plus 5 right here is 5, right? And this is the same thing as 3 times 1, 0 plus 5 times 0, 1. Okay? And this is 3i plus 5j. Vector u of 3, 5, you can think of as 3 of the I plus 5 of the j. So, okay. J right here, 5 times of j is that much, 5j. Okay, and I is right here, 3i is that much, right? So 5 of this plus 3 of this is going to be the vector right here. This is 3, this is 5. This point right here is going to be 3, 5. And it's really your vector u. Okay, as you know about the magnitude already, okay, and let's talk about this the use of vectors a little bit more. I don't think that the book talks much about this. And usually, I think it's used a lot in something like physics, whenever you want to talk about strength and direction. Say a person want to pull something, like a car trying to pull something with some force, okay, and we have an object, okay, right here. The first person tried to pull it up, pull it this direction. It's the force F1, okay, that much, and then you got help. You got help from another person, stronger force this way, F2. And you see how that object gonna move? Add the two vector F1 and F2. You use a parallelogram. The object gonna move this direction, F1 plus F2, with that much of the force in that direction. Okay? It's one of the uses. Try to demonstrate the work of vectors. All right. Now, let's recall something called the dot product. Dot product is a numerical value when you try to multiply two vectors together. Say v, I got another vector 3, 5. How about 1, 2? Okay. In 2D, right? So u dot v will be 1 times 3. I didn't write it in the right order. So 3 times 1 plus 5 times 2. You see, we multiply those number of components y's and then add them up. So 3 the x component times the 1 here, and then 5 the y component times the 2 here is the y component, and add them up. The answer is 13. This is the dot product of u dot v given in this example. And this is 2D. Of course, by similarity, you can figure out the same rule for 3D. You got z, okay? Say u here is equal to 3, 5, 1, and v here is 1, 2, -1. And guess what? U dot v is going to be 3 times 1 plus 5 times 2 plus 1 times -1. Okay? So this is 3 plus 10 minus 1 equal to 12. Same idea, just apply to z components as well. Okay. One more thing. Now that you have two vectors, think of it. This is vector u, and this is vector v. And keep in mind that we can shift those vectors around as long as they're parallel and have the same magnitude and it's the same vector. Next question. Is there any way that we can find the angle theta between the two vectors? The answer is yes. We have a formula for it. Cosine theta is equal to u dot v over magnitude of u times magnitude of v. Apply to both cases. In 2D or 3D is the same thing. So you want to calculate angle, first you calculate cosine. How do you calculate cosine? You dot the two vectors. You have a number in here, right? And you calculate the magnitude of u, you calculate the magnitude of v, you multiply them up, make a fraction. You have cosine, and then apply inverse cosine, you have the angle. Okay, apply to both 2Ds and 3Ds. Okay, last thing in this section is the first class. Oh, it shouldn't be too high. Is that okay if I stop right here? You think I can plug in a number? Say 2D right here. Is u is what? U dot v is 13, so the top is 13, right? And magnitude of u is square root of 3 plus 3 is 9, 25, and 34. And then square root of u is 34, square root. And then v is 1 plus 4 is 5, so square root of 5. And you multiply them out, you have the answer. And use calculator, apply what? Cosine inverse. You should have the value for the angle. Okay, now this is the last part for our clip today. We're going to talk about projection. Okay, projection. All right, say I got vector u. I got vector v. Okay. One thing before we mention projection. What if the two vectors make a 90-degree angle to each other? Say this is u, this is v. Then what? This angle theta, right? If the angle is 90 degrees, then cosine of 90 degrees, or cosine of pi over 2, by the way, is equal to 0. Is that right? And that means what? Cosine is what? Vector u dot vector v over magnitude of u times the magnitude of v is v. Okay? So equal to 0. It means what? U dot v equal to 0. And that gives us a hint. If you do dot product and the dot product equal to 0, that implies the two vectors are perpendicular, vice versa. Perpendicular, dot product equal to 0. Dot product equal to 0 imply angle is 90 degrees. Okay? Now, we're going to talk about projection. Say you got a vector v this way, you got a vector u this way. Okay? Put those two vectors with the same initial points. And if you want to project the vector u to the direction of vector v, it means what? From the tip of vector u, you draw a perpendicular line to v. And this vector right here is like the shadow of u on v. And they denote it this way. This vector is called the BROJ, stands for projection of vector u to the direction of vector v. Okay, let me double check and see if I write it the same way as the book. Yeah, that's right. This vector, the red vector right here, is called the projection vector of vector u on the direction of v. Okay, think of it. Think of red one is like the shadow of u on the v direction. Okay, and the length of that vector is, I don't know why the book gives you another notation. It's called this component of u on v. But all you have to do is what? Put the absolute value, just like the magnitude that you learned right here. And that means what? The length of that vector. Okay? Then last thing, how do you find projection of a vector on another vector if you know the two original vectors? Alright, so if you know u and v, projection of vector u on the direction of vector v is vector u dot vector v over vector v absolute value times vector v over absolute value of vector v. Or in short, people are going to write this way: u dot v over v square magnitude times vector v. And what is it about? This is what? Scalar. Okay, this is a number. U dot v is a number divided by magnitude is a number. Another number. A number divided by a number. You got a number. A number times v. Okay. This is a vector. It's going to be a portion of v. So this is the vector v is that much, right? So 1/2 of v is going to be that much. 1/3 of v, 1/4 of v is that much. So it's the number of vector v. And this is projection of vector u on the vector v. Are we good? You may see more. I can explain to you guys more about this. The unit vector is a vector that got the magnitude equal to 1, the length equal to 1. Okay, so I got a vector u of, say, how about this? 1/5 of 3 comma 4. I can write this way, or I can write 3 over 5 comma 4 over 5. This is the vector on the 2b, right? And you want to calculate the magnitude of u. Magnitude of u is going to be what? Square root of 3 over 5 squared plus 4 over 5 squared, which is 9 over 25 plus 16 over 25, which is equal to 1. See? Vector with the magnitude equal to 1, you call it the unit vector. It's just a name. Okay. And how do you get a unit vector in general if you have if you are given a random vector? Okay. Say I got another vector. Say vector v equal to 3 comma 7, for example. Then I can calculate the magnitude of v. What is magnitude of v? It is square root of 3 square plus 7 square. 3 square is 9, 7 square is, I think it's 49, right? 7 times 7 is 49, so this is square root of 58. Okay? So you have a new vector. Call it vector